Welcome back. Is this on? Oh, no, it is. Okay. So, welcome back. Third session today, Sustainability Through Clean Code by Emilie. And yeah, welcome back. Thanks for joining us again for a session. We look forward to it.
Thank you for having
Page
me.
is yours.
Thank you. So I'm going to talk a little bit about why it's important to talk about sustainability when we're talking about machine learning and AI. Then I'm just going to show some examples of why this is and what it means to some of the big models. And then I'm going to show you some examples of, how can we actually estimate or measure it. And then I'm going to start with something really simple, like how can I just use it in one of my tutorials? How can I then start using it for a slightly more complicated classification problem? And then how can I use it to improve code? Or how can I even use clean code principles to lower my emissions? So we try to create some good examples that really shows it. Now the demo gods were not with me yesterday. So I recorded this in videos, although if we want to and if we have time, it looks like I can easily jump into the machine learning studio and actually show you most of the code and what's going on. So if you're curious afterwards, at least that part we can definitely have a look at. But let's jump into it. So first, the big why. This is what the carbon dioxide has been in the past. And over here we've got 1950. And this is the current level of carbon dioxide in the atmosphere. So something is going on, and it's good to be aware of. Now, if we then look at where it's coming from, then electricity and heat are some of the main contributors. And when we think about what we do whenever we're using compute power, whenever we're using cloud, we are using energy. It's not always a bad thing. It's not so that all compute is bad, and I'll get into that also, but it's why it's so important to actually be aware that what we do, what we love doing, coding, machine learning, and AI, it can both contribute positively but also negatively. So what can we actually do when it comes to lowering the footprint of AI, and also when it comes to cloud and software? So we divided it up into sort of two branches because there is so much potential for using AI to actually reduce emissions and improve sustainability. Now that's not our focus today, but I could talk for hours about that too. Today we're going to focus on, well, how can we actually make machine learning code and AI more sustainable? We can do it with more efficient ML. And there are several ways to do it. There is local use, less data, also having really efficient models. Then there is also a trade-off sometimes between accuracy and efficiency. There can also be a way for humans and machine to help each other. And then, of course, there's also designing efficient software and also looking at where you're using your resources or compute. I'm going to give you some examples, but like we can see that Northern Europe contributes less carbon intensity when we're using compute than perhaps other areas. So that also matters. So we can use the same hardware in different countries, and then there'll be a difference in how much carbon dioxide actually comes out of our usage. Something I would highly recommend, and I think is really comprehensible and good to look at, is actually the principles of green, or on Microsoft Learn, their principles of sustainable software engineering. It doesn't take all that long to go through, and there are very many good recommendations in there. So of course is to build applications that are carbon efficient. And then the next is, of course, to make them energy efficient. Often we use energy as a proxy for carbon, but I'm going to get into why that is not fully true, and that is down to the next part, which is carbon intensity. So consuming electricity with the lowest carbon intensity is quite important, and then also trying to create solutions that are hardware efficient. Then there is also a proportionality between maximizing the energy efficiency. Then there can be something with networking. Let's say that my model is running on a compute in Korea. That might not be very efficient compared to having it running on a compute here in Sweden, which is now possible with Microsoft Azure. So that's one part. And then, of course, there is also shaping demand. Examples are you can have things running overnight or at times when we know that it's less carbon intensive. And then there is the measurement and optimization. And this is more of what I'm also going to show you today. How can I measure it? How can I see it? And what little changes can we actually make to improve this? Other possibilities that I'm not going to dive into today is having a look at the Green Web Foundation. Really love their work and what they're doing. And also so many good notebooks and examples over here on this GitHub repo on sustainable software engineering. So if you want the slides afterwards and the links, let me know, because there is a lot of good stuff out there. As we all know, the most important thing before we even get started is that we frame the business goal clearly. It's that we consider if there is already pre-trained services we can use, instead of training our own deep learning models. Today, a lot of people want to do that, and it's very fancy, but there can be a lot gained by using pre-trained services. Then there is the sustainable regions, which I also talked about before. Where do you actually put your compute? And then having a good data lifecycle policy in place. So, and then selecting efficient file formats and compression algorithms. And I'm going to show two very, very, very simple examples of having one piece of code that does a loop and uses a lot of compute, and another one where you have a vectorization with NumPy, and suddenly the compute is a lot less. So that's one of the examples. And then there is also the data movement across networks. This can also cost extra energy. So if possible, overall, if you can go for small data instead of big data, or at least start with small data, you are perhaps doing not only yourself, but also the environment a favor. Just have to look at the time that we get the important parts. Not only is it easier to work with, it's also easier to explain. It's also easier to visualize and expect. And then it can be easier for business users also to understand. So simpler is good, and I'll get back to that as part of the clean code principles, because simple is good is one of the main parts there. But if everyone can understand what is going on and in the data, it's easier for them to have faith in it also. So this is just a recommendation for small data rather than big. But there are many different parts of sustainable AI. There is one part that was what I just talked about, which is the data efficiency. So do we need it all to be labeled? Do we need a lot? Okay, we use few-shot learning. Great examples right now of few-shot learning is, of course, using ChatGPT or the OpenAI models that you heard of earlier today. I'm sure you mentioned that already. Instead of going on with our own learning. Then we can also do knowledge distillation. I'm going to take an example where we look at a bird and then a distill bird. So that is one of the examples you could use. But then responsibilities, of course, also fairness and privacy, but I'm not going to touch on that today. And then interpretability is easier with the simple models and with smaller amounts of data. So I really recommend this article. It gives a very good overview, and it also highlights very well how much can be gained when we use open source code and reuse the learnings of our colleagues. And why is this important now? Well, I think this drawing from the same paper shows it very well. This is the development until 2018 in how many petaflops per day these different deep learning models were burning. And over here we have the LBS of the CO2 equivalent. And here we can see that the big GPT-3 forerunner, the Da Vinci with 175 billion parameters, well, it burned something, I think it's close to 50 Danes' household energy consumption in a year. So, of course, if everybody wants to do this, that will have a big impact on the environment. And so, in an even more comprehensible manner, an average American generates 16.4 tons of CO2 emissions a year. An average Dane is about 11. And the carbon footprint of GP3 is roughly the footprint of about 50 Danes. So, yeah, that's why it's important. This is also a small overview, getting an idea of energy consumption and CO2 emissions. They are not a one-to-one, and that has to do with the carbon intensity. But at least it gives an overview over where we're at. So where we want to go is to simpler. What is simpler? Well, simpler models can do the job, and sometimes it's good to try to see if you can do that first. Regression models, it can also be decision trees for classification instead of running a neural network. It can also be doing a lot of modeling beforehand of the data, so you have a good idea, and so you won't be doing grid search because you don't have an exact idea of how to treat the data. So these are just some of the ideas, and these are also easier to explain. Right, so begin with a simple algorithm, start with the baseline, and then try to test. This is also what I'm going to show. One of the examples that we have is from training a bird model for International Red Cross. And here we figured out that we could actually work just as well with a distilled bird. It had 97% of the same performance, but it had 40% less parameters, and at the same time, it also ran 60% faster. So that is a good example of actually taking a very big model and having that distilled learning in a smaller model and getting just as far with that. So I thought that was a really good example. Also, pre-trained can be good and use that for transfer learning. Yeah, so start with small is the overall idea, and then try to select sustainable regions. But how can we actually measure the emission and the resource consumption? So what is it we can do in our code right now? Well, overall, it's what we're looking for is the electricity, and we're looking at the carbon. And the carbon footprint is the combination of these two multiplied. Now, some of the possible packages out there estimates, and some of them actually measure. So first, I'll show you MLCO2 impact. It does estimations. It's not as easy to use, but it gives you an idea. And it's good to give you at least also an idea of which regions are very carbon efficient. And then CodeCurrent, and there we're going to dive more into the code. So, great website, lots of good information, and you can actually learn a lot. And you can figure out what regions are good to choose. So definitely recommend to choose your region. You can also buy carbon offset, and it gives you a lot of good information on how to choose clean energy. But the downside with this one is that when you then go into the calculator, you can't choose all kinds of compute. There are several of the types of compute that I used that wasn't there. I can only put in hours used. I can choose most providers, yet when I do that, I will not get, I will get an estimate and not an accurate for each hour of the day. Yet I can get a sense, and I like that about it, of which providers were most green. And what I really like seeing here was actually that the carbon emitted by this simple example was already offset by the provider. So I get a pretty good idea that if I choose Asia or Northern Europe, actually I'm not contributing negatively to the environment. So at least for that, this one is fairly good. But then on to the one that I became a bigger fan on, which is CodeCurrent. Highly recommend visiting their website. It's a very lightweight software package. And it can very easily be installed in Python, and it can run. There is also an API, but it's in beta version. I tried to run it with the Designer and Machine Learning Studio, and it wasn't that wasn't quite as great. But it does run offline, it does run online, and they actually have a great repo with lots of good examples to get you started. So do take a look at that. And all you do is that you do your pip install, and then they have a couple of different ways that you can then start tracking. You start with the simple one, and then we're going to jump into getting more and more information. They also have a very nice site that actually tells you how to get started. It tells you how to do the installation. I'm doing the fairly simple one in Python. I highly recommend that. It worked every time. You can also install it with the Conda to be working in offline mode when you're just working on your own laptop. So, and that seemed to work well too. And then there are the possibilities of using first explicit object, where it will tell you for each of the objects that you're running how much energy you're consuming and how much carbon is being burned. Then there is the possibility to add it as a context manager or a decorator so that you can actually get more information out of it. But we'll see that now that we're jumping into it. So they look very much also at the carbon intensity that is consumed for the computation. That means how much CO2 is actually emitted per kilowatt hour of electricity, and then the power consumed in the computational infrastructure. And their calculation of the CO2 or carbon dioxide emissions are C times P. So that is the way they do it. Now the thing is that different countries have different carbon intensities. Even the same country have different carbon intensity over different parts of the day. So let's take Sweden as an example. You got lots of hydroelectricity, especially in the spring period. Whereas if you look at the summer period, it's a very different combination of energy that you have. Then we have countries like France, where they have lots of nuclear, and Denmark we like wind, but sometimes the wind isn't blowing, and then our carbon intensity also goes up. So it changes not just by country and region, but also time of year and time of day. Now, so this can be a little tricky to calculate. There is a good training on Microsoft Learn, and otherwise I'm also going to get back to using electricity maps, which is a startup that's doing a really good job at actually making some fairly accurate estimates. Those estimates are so accurate that they are used by Microsoft and Google for their dashboards for cloud compute consumption and CO2. Good. So there is also a carbon intensity API, but that's only for data in the UK. Electricity maps, really good. Highly recommend that. But if you want to start easier, I have to say every cloud provider, and I'm going to show you in a moment, provides a dashboard over your consumption and how much CO2 emissions has come out of it, and their data is actually based on electricity maps. So if you're lazy, you don't need to, you can see most of it there. And then there is also one called the What Time. That one I haven't tried out. If any of you tries it out, I'd love to hear your feedback on it. Now, back to the example of the BERT model, and why does it matter with the different areas at different times? Well, the example here is that if the BERT model had been trained in Norway, the CO2 emissions would not have been that high. Whereas if it had been trained solely in Germany or central US, we were at a whole different level. So this is pretty much, if you imagine that one household was about 10, then we go from being about one Danish household to being almost 3 Danish households, just in rough numbers, but to give a perspective on how big a difference it gives when you're in different regions at different times. Yeah. Good. And again, to give an idea of the most known models and where they're at, then here we have the fine-tuned BERT, which is somewhere in between driving a mile and having a gallon of gasoline, just for this part when you're using it. And this is then the LM-BERT. It's a bit more, but gives an idea of where we're at. Then I talked about the fact that there is already dashboards. So here's just examples of the biggest cloud providers' dashboards. So this is the Microsoft carbon emissions. Here I just go to Power BI and I use my authenticator, and then it can log into my Azure, and then it can see my consumption and pull it out and see how much I've been spending at different times. Google has a similar dashboard, not quite as much information, but it's there, and the same actually goes for Amazon. So starting to just get an overview, at least for your subscription and tenant, this will be all you need. And they use the information from electricity maps. Good, but let's jump into it. So I go into CodeCurrent, and I basically just copy the code. And then I go over to a classic training of an image classification using the MNIST dataset in Machine Learning Studio. And what I do is that I first install the other packages and then install the CodeCurrent. I add the little piece of code to do the tracking. And then all the way to the bottom, I again add my tracker so that I can be sure that it will be measuring all the way. Once I've done that, I am ready to have it start running. And that's it. That's the first start. So from there, we will see what it does. Now, why am I choosing, and I'm just going to jump onto the next slide, because the reason why I chose this tutorial first was because it's available to everybody and it's sort of a classic thing you do when you do a machine learning service. But also, classification is a classic logarithmic problem that we use, and where we're all the time trying to find a scalar product between two different weights. And that becomes relevant in my next example when I'm trying to look at vectors which have a similar way of doing the calculation, and where we're using clean code principles to lower the amount of emissions and compute that we're using. Well, let's go back into this one. So we put it in there. Now we'll go and train, and here it's important also to know that it's the training of the models that is really computationally expensive and not actually using the model in general. So that's why I choose the part that is for training. As soon as I start running it, it will start giving me information down underneath here where it says what I found, what kind of a CPU am I using, so what kind of compute. And then for every cell that I run, it will actually start telling me down underneath the compute that it can read from it. No. And then at some point this one takes about 5-10 minutes, and at that point I'm just going to skip over, this is like TV kitchen, to the next one so that we can see the entire consumed. But for every cell it's running, it's actually doing the calculation, telling you how much was for that cell, how much compute in total, and how much have you accumulated in this entire script so far. So this is the simple way of doing it, but it gives you a fairly good idea of how much you're running up. Any questions? All right. So there's a lot going on here, and I could probably talk to an hour if I was supposed to explain everything that was going on, but that wasn't my main focus. So that's why I also created 2 other examples, actually 3, where it's more comprehensible, easier to understand the code, where there is less going on. All right, I think that's cue to go on to the next part. See? Anyways, what I want to get to the part is that after I've registered my model, so I've done the entire training and it's gone correctly, down here in the bottom, it will now give me, oh, I can't jump in it. No, okay. Then I'm just going to cheat and say, you're going to get this. So I've run the model, it ran well. I could see for each of my coding boxes what was the CO2 that I was burning and how much compute and power was burned. And then in the end, it gives me this overview of, okay, the total consumed for RAM was 0.04 kilowatt hour, so not that much. And for all CPUs, 0.018 something. And all CPUs power were running on a 42.5 weight. And then I can see what was used since I started the script, so since the beginning. Now, this isn't very much, it wasn't very impressive, so let's do something that burns some more. Now, this is based out of a very, very good article I recommend from Towards Data Science by Kasper Rune, who's also a part of the Danish data science community. And he created these very nice overviews over how else can you actually get much more information out of CodeCurrent. So I thought, let's try that. So now we take a big, and I'm sorry for the format, maybe I can open it in a nicer format afterwards. But now I thought, okay, let's go in and take some of the heavy guns out without it taking forever. We're gonna use TensorFlow. We are again going to do some classification and deep learning on MNIST, and we are going to work with several layers. So we have both a flattened input shape, we have our dense layer, and then a dropout, and the 10 layers. And we're not going to do, it's going to do the epochs as it wants, and we're not telling it exactly what hyperparameters to go for. So this was for us sort of a normal example. It ran in about 7 minutes, and down here you have all the computation. Then you can start seeing all the different epochs, and you can see the loss and the accuracy and how it's improving for each of them. And then actually here comes the total kilograms this time of emissions. Now, because I used a different piece of code up here in the top, now it actually did a little log file for me that's hiding over here. Now, these aren't so nice when you look at them in here, so I have pulled them out in Power BI and just created a visualization so that we can compare the 3 models I'm showing you. This one is a little different. This time, we're now doing grid search. It's only going to run 1 epoch, but it has now specified exactly it's now going to try to optimize for all the different kinds of hyperparameters. So it's basically doing the same thing, but it's just going to burn a lot more compute, because it is going to do a lot more tries to test to find the optimal model, would be the simple explanation of that. All right, so here we're using the grid search. It takes a bit longer to run. And again, because I started with this piece of code up here, it will also write everything out into that. But we can see that it's doing a lot more steps and combinations, even though it's not doing more epochs. And we can see that it burns a little bit more for more CO2. Then I get these little CSV files up here, but they're hard to read in here. So I have downloaded them, and then I can show them to you from Power BI. But in here, I can actually see who's the cloud provider, what country are we in, what kind of energy consumption and so forth are we having. And then, just for the fun of it, I was like, okay, to make it easy to understand and illustrate, we're taking the same one, we're doing grid search, we're trying to do a classification on the MNIST data set, but this time, instead, I'm asking it to do 10 epochs, just to make it 10 times bigger so that we can see the difference. And here we can then see how for each of them, we now have the changes in the loss and the accuracy. So suddenly we have a lot more calculations going on. And it goes on and goes on and goes on, because now it's 10 times bigger, more than that. And now we can see that it's also become, yes, we got better accuracy, but the emissions has also gone up heavily. And what does it then look like if I take it over in Power BI and I make it look nice, and I just want to compare the sum of the emissions and the sum of the duration? Well, then this was the first little notebook that we were looking at, where it was just doing a normal kind of classification. This is when we do it with grid search, and this is then grid search with 10 epochs, just to get a feel of how much does it change the more times we run to get better accuracy. And this is the whole trade-off between, do we want higher accuracy, or when is it high enough, when is it good enough? There, you get a lot of more data out. I can also jump into, see how much time I have, into the Azure Machine Learning service to show you. But overall, you get the name of the project, you have the duration. This one is then not so nice, but some of the emissions, the sum of the energy, and you can also see that in totals. So, if we jump out of it, and then I'm hoping the demo gods are with me. No, okay, or maybe they are. Then we ran it over here, and then it created some nice little log files underneath here for us. Here we go. These are for the next example I'm going to show you, but nevertheless, you will get an idea. So this is what they look like, the files. And then what I did was I exported them out into Power BI so that we could look at them further. So we have timestamps and project. We've got duration, emissions, emissions rate, CPU or GPU, and also the RAM and the region and where we are. So that was just so that it became a little easier to understand. Then I wanted to see, because now you heard about OpenAI, and I thought, okay, I wonder if I can make it run on top of calling one of the OpenAI models. So this is a very simple little script, and the sound is missing. And this is the one thing I couldn't get to open and run when I came in. What we do is that we call the DaVinci text 002. We actually speak then to the system, and we ask it for, I also put in the CodeCurrent, of course, and I installed it first. And then we use speech synthesis from cognitive services to actually speak to it and ask for help on different tasks. Now the sound is missing, which makes it less fun. I'm sorry about that. I promise I'm showing it next week at Microsoft, and there the sound will be working. But what I wanted to show was just that even though you're not training a model, even though you're just using another model and you're using it via an API call, it can actually still tell you how much power is being consumed. Of course, it's far less because you're not doing training, but you can do it. And I thought that was fun to just show. And so I think I asked it how to do a good presentation. Let's see what comes out without getting you bored. Yeah, that one wasn't a winner. But I also said we would do something with clean code. So we were thinking a bit among ourselves, how could we create a good example with some math that everybody could understand and where we could see the difference in the code and then also in how much compute we were consuming and the CO2 that came out of it. So we thought, okay, the principles of clean code is, always follow standard conventions, keep it simple, stupid. Well, that's what it says. You can also read more here in this very good GitHub repo. Simple is always better, and reduce complexity as much as possible, and that does sound a lot like some of the previous things I said. Then there is a Boy Scout rule, leave the campground cleaner than you found it. That's a very good rule. I don't do that always, but it's good. And always find the root cause. So these are some of the main things to do. Then they also always say do small, do one thing, use descriptive names, fewer arguments, have no side effects, and try to not flag arguments. And then we thought, okay, how can we show this? And we thought, okay, well, when you have a logistic regression, you are looking at the weights and difference between them. It's not that difference from when you look at vectors. This is why you do all the vectorization. This is why you do all the matrix calculations. So we are going to do a little calculation where we're looking at a vector A and a vector B, and we're going to look at the distance between the two of them. Very simple. And then the first we'll do is a for loop, because that is classic programming, but it's also quite inefficient. And then after that, we'll do a calculation where we do a vectorization of it, because that is more efficient programming. And then in order to make it really clear, we scale it up by 10 times, by 10 times, by 10 times, so that you can really see how this becomes a major problem the bigger the model is. And to make it even more efficient, we are using the package NumPy. And again, that is also another good trick that instead of writing your own code, using packages is often much more efficient, because that is efficiently written and compiled. So that's also a good thing to do. So what does it look like? In this case, first we have our calculations where we're doing the loop for our scalar product. And we also set our tracker so that we will get the log outputs. Then we set the arrays. And then we ask it to loop through them and do the calculations and stop the tracker. Over here, same thing. But now, instead, we have the arrays, and we ask to do a vectorization with NumPy, and then do the calculation. And this was more because we thought it would be an easy thing that most people could somehow see or understand. So this is a bit of a long video. We get started, we install it. Here's the tracker that makes sure that we got the log files. Again, a good reminder of what we're doing with our scalar projection. Then the calculation in its essence that we're going to do a loop over. Here we then write out the log, where should we put it. Then we set the tracker. We do the code I just showed you. Then we stop it. Then we have the next where we're doing a much more efficient vectorization. Same thing, main code down here, stop the tracker, all right. And then in order to make it really clear, we make it 10 times bigger. So 10, 100, 1,000, 100,000, 1 million, 1 billion. Just so that we can really clearly see how much more does it then burn in compute and in carbon. I hope you're not, everybody with me still? Any questions? Okay, well, let me know. All right. And it runs and it runs and it runs, and now it starts getting heavy. Then we ask it to actually read the experiments, sum it up, so that we can see how it changed, and we have all the information that came out. And then we want to do a visualization of it, so that we can see what does it actually mean. And then it looks like this. So, if we did the loop, this was the kilo of CO2 emitted during computation, and this was the CO2 rate that we were at. If we did the vectorization, we were at a whole different rate. And we could actually see that although compute time is not completely one-to-one, there is a very strong correlation. It's not between the two. So that was just to illustrate this is a super simple calculation. This is a calculation that's included in pretty much all machine learning we're doing, and this is the difference between doing it efficiently with clean code and with bad code. Does that make sense? Okay, well, good. Then I also promised, and I can see that we actually have more time than I expected, so we can jump into it and many questions. I also promised, can you do ChatGPT for more efficient code? And I just asked it to pull up one example or two for me, and the answer for me was yes, you can. You can ask it both to give you an example of very shitty code, and you can ask it to give you an example of how can I organize this in an even better way. So we've used it a lot to take old, not so good code and either explain it, or can you rewrite it to a more computational efficient code. So far, we have very good experience with using ChatGPT for that. So although you shouldn't send sensitive data out there, this is, it works and it's efficient. So, give it a go and give it a try. Good. Now, overall, what I've been talking about today has mostly only to do with everything that's mostly going on here, our direct effects on global emissions, and not the entire supply chain. But once we are able to measure all these parts, then we can have a greater effect on the entire supply chains. So that was just to pull it out in a bigger perspective of the different scopes. And since we are only looking at compute and electricity, and we're only using at what we're directly doing, we're over here. If you are OpenAI and you are producing these models, or you are Microsoft, you have a lot of indirect effect on the world around you. So that's it. Good luck with your clean green coding. Any questions? I think we've got 10 minutes. And otherwise, now would be the time where we can actually jump in and have a look at some of them. Yeah. Yeah, it's a very good question. I haven't had that question before. So the first I think is, well, you've got your overall compute calculations if you're using a cloud, Azure or so, that fits. If you want to have something that is really made according to the EU directives, then Microsoft has developed a whole calculation form called the Sustainability Manager, but it's quite a lot of work to actually use that and do it. So I think I'm more up for the, making it clear what you do and showing what is the impact of the code that you're running. If it was for the EU directives and actually doing the accounting, then you would be looking at the overall compute from their cloud, and that would be the calculations you would be looking at. Does that, yeah?